Okay, so here we'll just take a few minutes to look at an old free response question. This is from the 2012 AP Calc AB exam, and it's problem number 1. And this is a problem that you would definitely been able to use a calculator on. And if you read the problem set up here, basically what you have going on is you have a hot tub that has water in it, and the water is being heated over time. And the temperature of the water has been measured at various values of T, and that's the information that we have access to in order to answer all the questions that were asked. They give us some information here that we'll need a little bit later on in different pieces of the problem. We'll just kind of jump right into part A here, which says use the data in the table to estimate W prime of 12. And so obviously you can kind of see my work that I've already done down toward the bottom of the screen, or in the middle of the screen here. And this looks like a slope calculation. And if you think about it, the first way that we computed or estimated derivatives way back in the fall was by saying that since a derivative represents the slope of a tangent line, we can use the slope of a secant line, or a regular old slope calculation, to estimate the value of a derivative. So to estimate W prime of 12, just take the two t values on either side of 12, take those two ordered pairs, so you have 9, 61.8, 15, 67.9. Do a slope calculation between those two ordered pairs, and you have your estimate once you've computed it. The units here, if you think about it, the units in the numerator, which would be values of the function, would be measured in degrees Fahrenheit. In your denominator, you have units of minute, just a difference in t values in that denominator. And so the units of our result are going to be measured in degrees Fahrenheit per minute. And it wants us to try and say a little something about what this means within the context that we're dealing here. And this set of units you'd hopefully recognize as representing a rate of change. So at t equals 12, the instantaneous rate of change of the water's temperature within the hot tub is approximately 1.017 degrees Fahrenheit per minute. As we move on to part B, what we're asked to do is estimate the value of a definite integral. So here's the definite integral that we want to estimate the value of, and what we need to use to do this would be the first part of the fundamental theorem of calculus. So if I'm trying to use the first part of the fundamental theorem of calculus, I'm going to find an antiderivative of this function, and then I'm going to put in these limits of integration and take a difference. So an antiderivative of W prime of t is going to just take us back to the original function. It's going to undo the derivative. Antiderivative undoes the derivative. So I need to evaluate this antiderivative, W of t, at 20, evaluate it at 0, and take a difference. So I can take information from out of the table to help me figure out what the value of this expression is going to be. So I'm just going to take W of 20 minus W of 0, get an answer of 16. The units here are going to be degrees Fahrenheit. We said in part A that the units of W prime would be degrees Fahrenheit per minute, and then the units of this differential dt are going to be the same units as t. So when you take the product of these, the minutes cancel with each other, and you're left with units of just degrees Fahrenheit on your answer. What does this represent within the context? Well, you took this temperature and you subtracted this temperature. So this answer represents the total change in the temperature of the water in the hot tub from t equals 0 to t equals 20. And if you think about it from more of a calculus standpoint, you'd take this rate of change, and when you integrate a rate of change, you get how much change actually happened across your limits of integration. So this is the rate of change of temperature. When we integrate the rate of change of temperature of the water, we get how much the temperature of the water has changed from this value to this value. When we look at part C, we're asked to use the formula for the average value of a function, which they were nice enough to give in this instance, and we want to use this formula and estimate the average temperature of the water in the hot tub by carrying out a left Riemann sum. So if you think about your data points, this would be a subinterval from 0 to 4. This would be another subinterval from 4 to 9, a third subinterval from 9 to 15, and a fourth subinterval from 15 to 20. So a Riemann sum is just going to have us adding together areas of rectangles. So if we're going to estimate the value of this integral, now we do have to keep this 1 over 20 here, but we're going to estimate the value of this integral with a Riemann sum. The first subinterval ranges with its t-values from 0 to 4. The left end point's here. So this function value is going to represent the height of the first rectangle. Here's the next subinterval. The left end point is 4. This function value is going to represent the height of the next rectangle, and then the width of that rectangle would be 5, the difference between these two t values. And then the next rectangle is going to have a height given by w of 9, and then a width of 6. The difference between 15 and 9 would be 6. And then add on the area of the last rectangle, which ranges between these two t values. There's the left end point, so that's going to generate the height of your rectangle, times the width of it, which would be 5 for the width, the difference between 15 and 20. When you compute this with a little bit of help from the calculator and then multiply it by 1/20th, you end up with 60.79 degrees Fahrenheit. If you looked at this graphically, and you can definitely draw the graph up front, I just kind of fit it in the bottom corner of the screen here just to make more sense of the second question that we're asked, and that's whether or not this estimate is an overestimate or an underestimate. Well, if you look at the graph, since W of t is increasing, the temperature of the water in the tub is increasing over time, these rectangles that a left Riemann sum would generate are all going to sit down below the function. They're not going to go up above the function at all. So we'd lose a tiny little bit of area here that should have been represented within the integral. We lose a little bit more here, we lose quite a bit more here, and then we lose a little bit more right there based on my kind of crude sketch of this function. So we've actually done an underestimate for the value of this expression. And then the last part of this is going to ask us to try and estimate the temperature of the water in the hot tub at t equals 25. Now obviously our data doesn't go up to t equals 25, but they've said that this function here is going to represent the rate of change of the temperature of the water in the hot tub across the interval from 20 to 25. And if we want to figure out how much the temperature has changed from 20 to 25, we're just going to integrate that rate of change. And to estimate the value of this, if the calculator's in play, do this integral on the calculator. So I have my calculator ready to go here, and I actually have my answer here already. Clear that off and get it one more time. So if I'm going to try to generate this answer on the calculator, I'm going to go into my math menu and grab my numerical integration feature from the bottom of it, and I'm going to get my integrand in first. So I'm going to have 0.4 times the square root of, and I'm going to have an x in place of the t, and that's fine, you've seen that happen a bunch, and then times cosine of 0.06 times x, and again the x is in place of the t. So there's my integrand. The next part of this call sequence is a comma, and then the variable that we're supposed to integrate with respect to. Well, I'm going to integrate with respect to x since that's the variable I just typed into the calculator. Next part of the call sequence is another comma. Then I need to give the calculator the lower limit of integration, which in this case is a 20. Then I need another comma, and then I need to give the calculator the upper limit of integration, which is 25. Close my initial parenthesis, hit enter. This is how much the temperature has changed over the course of the time interval from 20 to 25. Tack on the temperature of the water at 20, and this is how much the temperature of the water would be at t equals 25.